What we're going to talk about today is PIDs and how to tune them. I've written a basic PID loop for all three motors, the Coxa, femur, and tibia. Once that's written, there's a variable associated with each one of these, the PID, the proportional, integral, and derivative, that has to be determined, and the only way to do that is through testing. So the method I used to do this, I kind of gleaned out of some research and putting it into effect. So what I'm going to do now is show how I tuned the loop initially. I'm going to do with the Coxa motor, since that's the one that seems to be most sensitive to the inputs for these variables. To start with, the way that it's going to be tuned is I'm going to set the integral portion of this equal to 0. Now, in reality, this setup that I have on this is I did not use the derivative at all. It turned out it's really not necessary for the short runs that these things are actually making. The motors aren't moving long enough to make a derivative really effective. So it was actually a PI loop. So to start to make this thing work, to tune it, we're going to go ahead and set the integral portion to 0. Basically cancel it out. We're going to go with the proportional portion first. I'm going to start with a low value, and the concept here is to increase that value until I start seeing oscillations. Once I see oscillations, then I'm going to back off on that value. Right now the Coxa position is sitting at the 90 degree. We're going to move it to the 100 degree position, and we're running with an initial constant of 1, and this is the result. As you see, it's a very slow moving to the position. Now what we're going to do is increase that value to 2. Alright, we're going to move the Coxa motor back. This is with a constant of 2. As you see, it's much quicker and looks pretty good. So that isn't bad. Let's go with a value of 3. Here's a Coxa movement with the variable equal to 3. I got a little bit different movement, a real fast start and then a slow coming in to it. So going back up again, we're now set it to 4. Alright, now you can see with 4, all of a sudden it's very fast, but a lot of jerk in the movement when it gets to its position, and a final back and forth associated with it. So now we're getting oscillations. Just to show how that went, let's go and change it up to a 5 and see how that increases. Yeah, it's even more pronounced there. So basically the last good value for this was a 3. So we're going to set our proportional value constant equal to 3, and we're going to do the same thing now with the integral portion by basically increasing the value until we get oscillations or unwanted behaviors. Initial test, we're going to use a value of 1. Now in the integral portion, this actually is a 0.1 because I divide that value by 10. The reason I set it up as divided by 10 is I wanted to do total integer math without having to get into using floating point, since I don't have any extra cogs available to run floating point software. So I run this with a whole number of 1 for the value, then divide it by 10 when it gets to the actual output. So showing it at 1, let's run this, move it back to a value of 90 degrees. Okay, we're getting some movement back here, and when I look at the troubleshooting display, it is bouncing back and forth. Direction is changing. So let's go and increase this and see what we get next. Okay, there was with a value of 2 or 0.2 as far as the system is concerned. And looking at the troubleshooting screen, I don't see any oscillations. It moved pretty quickly, yet the only jerking back and forth is actually just mechanical in there. The motor itself was not bouncing back and forth, which is a good sign. So it's looking like our value is going to be probably between 1 and 2, or again 0.1 or 0.2. Just to validate this, let's increase it to 3 and see what the results are. We can see that it's bouncing back and forth. Let me show you. As you see, it's oscillating and finally finds a spot and gets it within the dead band and stops. So very bad situation in that. Alright, looking at the troubleshoot screen, you see that at the top, basically, when we start it up, it tells me what the slope of the is, the encoder value, and the calculated angle. Remember, this thing is all, so where you see the Coxa is 100 or 1002. It actually translates to put a point in there, so it's 100.2 degrees. So when we start out and we say requested angles at 900, so we go Cox angles at, again, the 1002, the amount of move it wants to make, as far as the target value that it's going to go to, and the slope. Then underneath that, we start with the encoder, the target, the amount of error, the speed at which it's going to go, the direction, and this is what I'm looking at right now, and then some other information telling me here's what the KI value is and the error summation. The integral portion is a summation, and that's what the error sum is. As you see, it rapidly increases up to 500, and 500 being the maximum I allow on this. But the important thing is you see the direction, how it starts out as 1, and then it overshoots, and it goes to 0, which means it's now reversing the motor to go back to find the actual value I want. We wanted to not have any reversals.